So you've written a program, it works, everything's great. But if you've got a loop that happens to go on slightly longer than it ought to go on for, that means your program's inefficient. We're going to look at ways of addressing that, and we're going to look at what we can do to recognize when a loop could actually terminate a little bit earlier. If we can do this, our programs are always going to be much more efficient and they're just going to run better. Okay then, so the way this is going to work, I am going to write a program that is going to test whether a number is a prime number or not. Quite a simple program. I'm going to write it in Python. We're going to use mu to do it. So just watch while I write the program. Okay, so it's quite a straightforward program. Let's just quickly talk through it so we all understand exactly what's going on. We're going to take a number that is going to be our input. We're going to make sure that we cast it as an integer because we're going to need to perform some maths on it. And then we're going to set a flag that is going to say that we're going to assume the number's prime, basically. So we're going to set that flag to true. So the first thing we're going to do is assume the number's prime, and then we're going to actually loop through every number from 2 up to 1 less than whatever the input was. And we're going to divide number by each of those values. So we're going to use the mod operator to take the remainder. If there is no remainder, as in whatever the value of n is divides directly into our number with nothing left over, no remainder, it means that that number must be a factor or is a factor of whatever the input was. Therefore, the number's not prime. At the end of the loop, we're just going to say if it is prime, we're just going to output number is prime. I'm going to take that space out there. Otherwise, we're going to say number is not prime. So we'll just test it with a few things. If I input 5, 5 is prime. We know that to be true. 21 is not prime. Now, I've deliberately written it so that our loop goes on way longer than it needs to. And there's a few things that we can do in order to improve this. And first of those is to ensure that we are being clever about the range that we're looking at. If the number divides by 1, it therefore divides by itself. If the number divides by 2, 2 goes into it, that means half of that number also goes into it as a factor. And if we use that, we can then look at all of the pairs of values. That therefore means the smallest number that could go into it is a 2. And therefore, the largest number that could divide into it is half of that number. So what we need to do is, rather than loop up to 1 less than the number, because none of the numbers above a half are going to divide into it, we can just go up to half of that number. So if I just do /2, that'll give me half of that number. Now, a little tip, I might want to actually use a double / because that's going to behave a little bit differently. If I divide a number and I use a single /, it's going to give me a number with a fractional part. And I obviously have got no interest in trying to divide the value by 5.5, for example. If I use a double /, it's always going to round the number down. It's actually the exact opposite of mod. So we're going to always take the integer part of what we get as a result. We're going to ignore any fraction, ignore any remainder that we've got. And this will execute a little bit better. 5 is prime. And we'll test it again with the same number. 21 is not prime. Now, I've just gone back to the code that we had originally because I'm going to now implement a counter that's going to show us exactly how long this loop goes on for every single time. And then we can see how we're actually being a lot more efficient about the number that we're working with. I'm going to set a value which is going to be count is equal to 0, and I am going to say that every time I do a loop, I'm just going to say count equals count plus 1. And then after I'm done with that, I'll say something like print found this out in count attempts. So if we run the code, when we do it in 5, It found it out in 3 attempts. It tried to divide 2, 3, and 4. If I do 21, you can probably guess how many it's going to be. It'll do it in 19 attempts. So if I do my double forward slash, I can test it with 22. And this time it did it in a lot fewer attempts, did it in 9 attempts. Now, we don't actually need to go up to halfway either. Let's take the number 16, okay? We know that it's got a factor 2, and we know that its pair is 8. It's got another factor, which is 4, and the other factor that pairs with 4 is also 4. Therefore, we only actually need to loop up to the square root of any given number. The easiest way to find the square root without importing any libraries or math or anything like that is you will raise it to the power of 0.5. So number raised to the power of 0.5 is going to give me the square root. And to raise a number, in case you don't know that, you will use a double asterisk. So if I run that and I'll say 5, it's not going to work because I need to cast it as an integer, which is kind of obvious. I should have spotted that before. If I run that, 5 is prime. Run that again. 21 is not prime. And this time it only did it in 2 attempts. If I run this again, let's try number 31. 31 is prime. It found that out in 3 attempts. This is now a lot more efficient. Now, you might have been screaming out all the way through this that there's another thing that I can do to improve my efficiency. And it's actually to change the nature of the loop that I'm using. I've got 2 kinds of loops available to me in Python. One of them is a for loop, which is to be used when you know how many times that loop needs to be completed. So we know that we're going to go from 2 up to the square root, or we're going to go from 2 up to halfway, or we're going to go to 2 up to 1 less than the number that we're investigating. But we could convert this to a while loop, and it means that we've got an extra way of breaking out of our code. I am going to implement n and start it at 2. And I'm actually just going to change this, and I'm going to say while n is less than or equal to the expression that we had for a number raised to the power of 0.5 and cast as an integer. I am also going to ensure that, as well as incrementing count, I'm also going to increment n as well, because we need n to obviously get up to the value in order to break out of it. Now, I know that I could have done the for loop using a break and I could have escaped it that way, but I actually prefer to change the logic because it makes it easier to read for me, for when I'll come back to this code later, but also if you're working with somebody, this is just a lot more clearer, and it means that your code's just going to be more maintainable. But if I take a very large number, for example, I've got a W in there, let's just take that out, and I'm going to end it in a 2. Okay, this is going to take a long time to complete. Okay, and in fact, I'm not actually interested in seeing how long it takes. However, because I know it ends in a 2, I know it's an even number, I can tell, because I'm a human and I can use other things that I can infer from the number that we're looking at, whether or not it's prime. But a program has to step through from line 1 all the way up to line 18. We're going to change this again slightly and make another way that we can break out the loop if we determine it's a prime number. So at the point that we determine it's prime, we're just going to escape. Now, we've already got a flag that can do that for us. So we start with assuming the number is prime, and when we prove that it is not, we're going to just set that to false. Now all I need to do is I need to say that while that criteria is true and while prime is equal to true. If I run that, 5 does it in 1 attempt. However, my very large number that ends in a 2, it determines it in 1 go. That's a lot more efficient. The code still does exactly the same thing. It just means that we're not entering into very, very large loops. Thank you for watching, and I hope you learned something. Please subscribe and write in the comments below. Tell me what you want me to investigate and what you want me to look at with you, and I'll try and explain it in hopefully as clear a way as I have done today.